The universe looks like it is built on perfect logic. Every particle, every force, every interaction follows strict mathematical rules. Nothing seems random at the deepest level. Physics describes everything with equations that work with extreme precision down to scales smaller than atoms. Yet inside those same equations, something strange appears. If you change even the smallest value in those rules, the entire universe stops working. Not slightly different, not unstable, completely impossible. Atoms would never form. Stars would never ignite. Chemistry would fail before it even begins. Even space itself would lose structure. And this is not speculation. This is what modern physics quietly reveals when scientists test how sensitive our universe is to its own laws. So a question begins to rise, one that does not go away easily. Why does anything exist at all if physics says it should not be able to exist in this form? This is not a philosophical question anymore. It comes directly from scientific models of reality. And according to a growing number of physicists, including ideas discussed in theoretical physics circles like those of Brian Greene, this is one of the deepest unresolved mysteries in science. Because the universe does not just exist. It exists in a way that seems extremely precise, almost fragile, as if one wrong setting would collapse everything. Take gravity, for example. If it were slightly stronger, the universe would have collapsed into a dense, hot chaos shortly after forming. No stars, no galaxies, just a violent collapse of matter. If it were slightly weaker, matter would spread out too thin. Gravity would never gather gas into stars. The night sky would be empty, cold, and structureless. Now look at the electromagnetic force. It controls how atoms hold together. If it were slightly different, electrons would not bind properly to nuclei. That means no stable atoms, no molecules, no chemistry, no life. Even the strong nuclear force, the force that holds the core of atoms together, is balanced with extreme precision. A tiny shift and either everything falls apart or everything locks into unbreakable dense matter where stars cannot function. It is as if the universe is balanced on a knife edge. And this is where the tension begins. Because science does not usually deal with just right conditions. In most physical systems, small changes lead to small effects. But in the universe itself, small changes lead to total failure of existence. This is known among physicists as the fine-tuning problem. The universe appears fine-tuned for structure, fine-tuned for stars, fine-tuned for chemistry, and ultimately fine-tuned for observers who can ask questions about it. But there is a problem. Fine-tuning is not something physics easily explains. It raises a deeper question that still has no confirmed answer. Why are the constants of nature set in a way that allows complexity to exist at all? Some scientists argue this could simply be luck, a rare set of conditions that happen once in one universe out of many possible outcomes. Others suggest something far more complex may be happening beneath the surface of reality. And this is where modern theoretical physics becomes even more unsettling, because the more deeply scientists study the structure of reality, the more it seems that our universe might not be the only possible version of existence. There may be many universes, each with different physical laws, different constants, and completely different outcomes. In most of them, nothing stable would ever form. In some, time itself might not behave the way it does here. In most, life would be impossible from the very beginning. And if that idea is correct, then our universe is not special because it was designed that way, but because only universes like this can contain observers who can notice they exist. But even that idea does not fully resolve the mystery, because it still does not explain why any universe exists at all, or why the rules of physics are structured in a way that allows universes to exist in the first place. And this is where the discussion becomes even deeper. Physicists like Brian Greene often point out that the universe is not just physical, it is mathematical. The laws that describe reality look like equations that could exist independent of anything physical. as if reality is built on abstract structures that do not depend on space or time. This leads to one of the most unsettling ideas in modern science. That existence itself may be far more fragile and far more precise than we ever expected. And if that is true, then the question is not just why the universe exists. The question becomes why it exists in a form that allows anything to exist at all. This video will take you through that mystery step by step. We will explore why the basic laws of physics appear so precisely balanced. We will look at what happens when those laws are changed even slightly. We will examine ideas like fine-tuning, multiverse theory, and the strange mathematical structure of reality itself. And we will explore why some of the most respected physicists in the world believe that something about existence still does not fully add up. By the end, you may see the universe not as something simple and expected, but as something that sits on the edge of possibility. And that is exactly why this question matters. Because the more we understand physics, the less obvious existence becomes. If you are interested in uncovering these deeper layers of reality and exploring the biggest unanswered questions in science and space, make sure to subscribe to the channel. There is much more ahead, and the mystery is only getting deeper. The universe looks stable from the outside. It feels permanent, almost predictable. But when scientists break it down into its most basic rules, a different picture appears. Everything depends on numbers that are fixed with extreme precision. These are called physical constants. They control how the universe behaves at every level. Gravity, light, atomic structure, nuclear forces, all of it depends on values that never seem to change. And here is the strange part. Those values are not just important, they are incredibly sensitive. Even a tiny shift in them would change everything. Start with atoms. Atoms are the building blocks of all matter. If the balance between the forces inside an atom changes even slightly, electrons would not stay bound to nuclei. Matter, as we know, it would not form. No stable elements, no chemistry, no solids, no water, no planets. Then come stars. Stars exist because gravity pulls gas together until nuclear fusion begins. That process depends on a very narrow balance between pressure and heat and gravitational strength. If gravity were slightly stronger, gas clouds would collapse too fast. Stars would burn violently and die quickly. The universe would become unstable and short-lived. If gravity were slightly weaker, gas would never compress enough to start fusion. Stars would never ignite. The night sky would be filled with cold clouds that never form structure. In both cases, galaxies fail. Structure fails. Time has no stage to build anything meaningful. There is also the nuclear force inside atoms. It holds protons and neutrons together. This force is incredibly precise. If it were slightly stronger, atoms would fuse too easily, creating a universe filled with only heavy elements. No chemistry diversity, no stable life conditions. If it were slightly weaker, even simple atoms would fall apart. Hydrogen might be the only element that survives. That means no complex matter at all. Even light is tied into this balance. The way photons interact with matter affects energy transfer across space. A small change in electromagnetic strength would break this interaction completely. Energy would not move in stable ways. Stars would not shine in a controlled manner. Each of these constants seems independent, but together they form a system that is tightly locked, a system where every part depends on the others being exactly right. This is where scientists begin to notice something unusual. The probability of all these constants landing in a life-permitting range at the same time appears extremely low. Not just rare in a casual sense, but mathematically narrow, like a set of dials all being tuned perfectly without error. There is no known mechanism in physics that explains why these values have these exact settings, and yet they do. This creates a quiet tension inside modern cosmology, because physics normally does not rely on perfect conditions. It relies on systems that can vary, adjust, and still function. But the universe does not behave that way. Small changes do not create small differences. They create total failure, which leads to a deeper question that scientists cannot ignore. Why is everything set in a range that allows structure, stars, and chemistry to exist at all? Scientists describe this situation with a simple term: fine-tuning. It means the universe appears to be set with extreme precision, where the basic rules of physics are adjusted in a very narrow range that allows everything we see to exist. At the center of this idea are four fundamental forces. These forces control every interaction in nature. They are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each one plays a different role, but all of them are locked together in a delicate balance. Gravity shapes the structure of the universe. It pulls matter together. It forms stars, planets, and galaxies. Without gravity, nothing would clump. The universe would remain a thin spread of particles with no structure at all. Electromagnetism controls how atoms and molecules behave. It determines how electrons bind to nuclei. It is responsible for chemistry, light, and every form of material structure. The strong nuclear force holds the nucleus of an atom together. Inside every atom, protons naturally repel each other because they have the same charge. The strong force overcomes that repulsion and keeps the nucleus stable. The weak nuclear force controls certain types of radioactive decay. It plays a key role in how stars burn and how elements are formed inside them. Each force works independently. But the surprising part is how precisely they must align for a universe like ours to exist. If the strong nuclear force were slightly weaker, atomic nuclei would not hold together. Hydrogen might be the only stable element. That means no complex chemistry, no carbon, no oxygen, no life. If it were slightly stronger, nuclear reactions would happen too easily. Stars would burn through their fuel almost instantly. The universe would become unstable long before life had a chance to develop. If electromagnetism were even slightly different, atoms would not form stable structures. Electrons might not stay attached to nuclei. Matter would lose its shape. Everything would become unpredictable at the atomic level. If gravity were stronger, the universe would collapse too quickly into dense objects. If it were weaker, stars would never form. Both outcomes lead to a lifeless universe. Even the weak force plays a critical role in stellar life cycles. Without its precise strength, the process that powers stars and creates heavy elements would break down. That means no elements beyond hydrogen, no building blocks for planets or biology. What makes this even more striking is how narrow these acceptable ranges are. Scientists have found that even extremely small changes in these constants lead to universes that are completely unlivable. This is not about slight differences in conditions. It is about total breakdown of structure itself. And here is where the tension grows inside physics. There is no confirmed explanation for why these four forces have the exact strengths they do. They are not derived from a deeper known law. They appear as fixed inputs to the universe. This leads to a difficult question that sits at the edge of modern science. Are these values random outcomes of a vast cosmic lottery, or are they pointing towards something deeper that has not been discovered yet? One of the most debated ideas in modern physics appears when scientists try to explain fine-tuning. If the constants of our universe are so precise that small changes would destroy everything, then one possible explanation is that our universe is not alone. This leads to the multiverse idea. The multiverse is the concept that our universe could be just one region in a much larger reality. A reality filled with many universes, each one existing with its own set of physical rules. In this framework, there is not just one version of reality. There could be an enormous number of them, possibly infinite, and each universe could have completely different properties. In some universes, gravity might be stronger or weaker. In others, electromagnetism might behave differently. Some universes might not even have stable atoms. Others might never form stars at all. There could be universes where time flows differently, or where space has more or fewer dimensions. Some might collapse instantly after forming. Others might expand too fast for structure to ever appear. In most of them, nothing stable would exist. But here is the key idea behind this theory. If there are many universes with different physical constants, then it is not surprising that at least one of them has the right conditions for complexity. In that case, observers would naturally appear only in universes that allow observers to exist. This creates a selection effect. Only universes capable of supporting structure and life would have anyone in them asking questions. That means the reason we see such a finely tuned universe might not be because it was designed or chosen. It might simply be because only in such a universe could anyone exist to notice it. This idea changes the way fine-tuning is interpreted. Instead of being an unlikely miracle, it becomes a statistical outcome across a vast range of possibilities. However, the multiverse idea comes with a major challenge. There is currently no direct experimental evidence that other universes exist. They are not observable in a simple way. They do not interact with our universe in any known measurable method. Some versions of the theory come from inflationary cosmology. In that model, space expands rapidly in different regions, possibly creating separate bubble universes. Other versions come from quantum physics interpretations where every possible outcome branches into a separate reality, but none of these ideas have been confirmed in a way that satisfies direct scientific verification. This creates tension inside physics. On one side, the multiverse offers a possible explanation for fine-tuning. It provides a framework where the precision of our universe is not unique, but one result among many. On the other side, it raises a problem. Science relies on testable predictions. If something cannot be observed or measured, its status becomes uncertain. Still, the idea remains in serious discussion because it addresses a question that otherwise has no clear answer. Why do the constants of nature fall into such a narrow range that allows everything to exist? And if there are many universes, each with different rules, then another question emerges. Why does this particular universe have rules that not only allow matter, but also allow complexity, stars, chemistry, and eventually consciousness to appear? At the deepest level of physics, reality stops behaving in a way that feels stable or predictable. The classical world looks solid. Objects have clear positions. Events follow clear causes. If something happens, it has a clear reason. This is how everyday life appears to work. But when scientists look at the smallest scales of reality, that structure begins to break down. Quantum mechanics replaces certainty with probability. Particles do not have fixed positions in the same way larger objects do. Instead, they exist in a range of possibilities. They behave like they are spread out in multiple states at once until they are measured. This is not a philosophical idea. It is confirmed through experiments. Particles like electrons and photons do not follow single paths. They behave in ways that only make sense when described using probabilities. One of the lesser-known details is how extreme this uncertainty becomes at small scales. In quantum systems, even energy levels inside atoms are not fixed in a simple way. They exist in discrete steps, but the transitions between them follow probabilistic rules that cannot be predicted exactly, only calculated as likelihoods. This leads to a strange outcome. Reality at its core does not seem fully determined. Instead, it appears to unfold through probabilities. One of the most famous examples is the double-slit experiment. When particles are not observed, they behave like waves passing through multiple paths at the same time. When they are observed, they behave like single particles taking a specific path. This raises a deep question that still does not have a clear answer. Why does observation change the behavior of reality? Some interpretations suggest that measurement forces a quantum system to take a definite state. Others suggest that all possibilities still exist, but we only experience one outcome. There are even interpretations where reality is not fully defined until it is observed. In those models, the act of measurement plays a fundamental role in shaping what becomes real. But none of these interpretations are universally accepted. Quantum mechanics works perfectly in predictions, but its meaning remains uncertain. Another lesser-known fact is that quantum fluctuations exist even in empty space. What seems like a vacuum is not truly empty. It is filled with temporary energy changes that appear and disappear constantly. These fluctuations are measurable and have real effects, including contributing to forces between objects at very small distances. This means that even nothingness is active at the quantum level. All of this leads to a deeper shift in how reality is understood. In classical physics, the universe is fixed. It evolves, but its state is always definite. In quantum physics, the universe is not fully fixed until it is observed or interacted with in some way. This challenges the idea of a single, solid reality. It raises a more unsettling possibility, that what we experience as reality may not be a single, fully defined structure. Instead, it may emerge from deeper layers of probability and interaction that are not directly visible. And this leads to one of the most profound questions in modern science: whether existence itself is something fundamental, existing independently at its base level, or whether it is something that emerges from deeper mathematical or informational rules that do not resemble reality as we perceive it at all. As physics goes deeper, another unusual pattern begins to appear. The universe behaves as if it follows rules that look very similar to computation. Everywhere scientists look, they find structure that can be written in mathematical form. Forces, particles, energy, and even space-time itself can be described using equations. These equations are not just approximate, they are precise and predictive. This has led some physicists to notice something unusual. The language of physics starts to look like the language of information. At the smallest scales, nature does not seem continuous in the way everyday experience suggests. Energy comes in discrete packets. Particles exist in quantized states. Even space-time, in some theories, appears to have limits below which it cannot be divided further. This idea becomes even more striking when looking at black holes. Black holes do not just contain mass. They also store information. In fact, one of the most surprising discoveries in modern physics is that the surface area of a black hole, not its volume, determines how much information it can hold. This led to the idea that information may be more fundamental than matter itself. Some theoretical work suggests that the entire universe could be described in terms of information processing. Every particle interaction could be seen as a transformation of data according to fixed rules. This creates a new way of thinking about reality. Instead of seeing the universe as a physical object that happens to follow mathematics, some scientists consider whether the universe is mathematics. Or even more radically, whether it is a system that computes itself through underlying rules. In this view, space and time are not primary. They may be outputs of deeper processes. Reality could emerge from something more abstract, similar to how images and worlds appear from code in a computer system. This leads to the information-based interpretation of physics. In this interpretation, everything that exists could, in principle, be described as information being processed. Even physical laws might be seen as algorithms that govern how this information evolves. One lesser-known detail is that some equations in physics already behave like computational rules. Cellular automata, for example, are simple systems where basic rules create complex patterns over time. Some physicists have explored whether similar rule-based systems could generate the structure of the universe. However, this idea is highly controversial. There is no experimental proof that the universe is a simulation or a computation. It remains a philosophical and theoretical possibility, not an established scientific fact. Still, it raises difficult questions that overlap with fine-tuning and quantum mechanics. If the universe follows rules like a program, then why do those rules exist in the first place? And why do they produce a system capable of complexity, structure, and observers who can study those rules? Even more unsettling is the question of whether those rules could have been different. If they are like code, then slight changes in the code would produce completely different realities, or no stable reality at all. This connects back to the earlier problem of precision. The same precision that appears in physical constants also appears in the structure of mathematical laws themselves. It creates a strange overlap between physics and information theory, and it leaves an open question at the center of modern science: whether reality is something material at its core, or whether material existence is simply one expression of a deeper informational structure that underlies everything we observe. Across everything explored in modern physics, one pattern keeps returning. The universe should not be easy. At every level, from the smallest particles to the largest cosmic structures, reality depends on a set of rules that sit in an extremely narrow range. If those rules shift even slightly, matter stops forming, stars stop shining, chemistry breaks down, structure disappears, and yet structure exists. The universe is not empty chaos. It is organized. It is stable enough for galaxies, planets, and eventually life to form. It follows precise mathematical laws that allow complexity to emerge from simple beginnings. This is where the tension begins to build. Fine-tuning suggests that the basic constants of nature are set with extreme precision. Quantum physics shows that reality is not fully fixed, but built on probabilities and uncertainty. The idea of a multiverse suggests that there may be many universes, each with different rules, and only a few that can support existence. The information perspective suggests that everything might be built from deeper rules that look more like computation than physical matter. Each of these ideas points in a different direction, but all of them agree on one thing. There is something about the structure of reality that is not fully understood. The deeper science goes, the less simple existence becomes. What once looked like a stable, predictable universe now appears more like a carefully balanced system that sits on the edge of possibility. And through all of this, one fact remains unchanged. We are here, not only inside this universe, but capable of studying it, capable of questioning its structure, capable of uncovering laws that describe reality at scales far beyond everyday experience. That creates a final layer to the mystery. The universe is not just something that exists. It is something that produces observers who can think about its existence. So the question shifts. It may no longer be only about why the universe exists in this form. It may be about why existence itself allows reflection on existence. Whether this balance comes from chance, from deeper necessity, or from something still completely unknown remains open. Physics continues to push closer to answers, but each answer seems to reveal another level of uncertainty beneath it. And that is where the mystery stands today. If this journey into the structure of reality brought new questions to mind, make sure to like the video and subscribe to the channel. There is much more waiting ahead, and the deeper layers of the universe are still far from fully revealed.